Okay. Hello, everyone. Thank you for coming in number, and thank you for those watching online. Welcome today to the first DIGISPORT research seminar. So we're going to talk today about sprint start, and we are delighted and very honored to have our friends from Ireland. I mean, Drew's a Scot, but he comes from Ireland. So you will have today 3 presentations talking about sprint start in general, and I hope it's going to trigger some discussions from you guys. So we're going to have Professor Emeritus Drew Harrisson, who's going to start and who's going to explore and explain everything he has started through the FAST project, which is something that talks very loosely, and you'll see he's going to explain that in much more detail about sprint start. Drew has been head of department, the president of the biggest biomechanics associations, the ISBS. He's a honorary lifetime member, I think. He's authored many research publications, but he's also a coach, a high-level athletics coach, and he's got that dual hat that we like here in Rennes at the confluence between sports science and applied sports research. Next, we'll have Dr. Evan Crotty, who's going to talk to us about his project that's exploring a bit more in details the neuromechanical delay within the sprint starts theme. And last but not least, we'll have Matthieu Milloz, who you've seen because maybe you've had a class with him. He's been in Rennes for the past year, back to Rennes because he actually studied his master's here. And then after all that, we'll have some Q&As, question and answers, that will take us back to the end of the afternoon. So without further ado, Drew Harrisson, thank you.
Thank you. Thank you. Good afternoon, everybody. Can you hear me at the back? Yeah. So thanks for coming here. I'm delighted to talk to you about the FAST project, and you might wonder, well, what is the FAST project? The word stands for Feasibility Analysis of Sprint Start Technologies. And what I'm going to do is to talk through the evolution of this project. It's a story, and the fine details of other parts of this project will be explained by Evan and Matthieu. But I just want to tell you a story about our project and how it evolved, because I think it tells us about how research comes from practice and eventually might influence policy. And it's a long story. It's lasted nearly 8 years, 9 years that we've been working in this project. And the project, I'll just... Sorry, it's good. Oh, wrong one. So it's a long story, and what I want to do is to tell you the starting point up to the point we are at now. Okay, there we go. So the FAST research team at the moment consists of all of these people. There's me as the principal investigator. There's Thomas Barr. Now, Thomas is one of the athletes I've coached for the last 11 years. He was 4th in the Olympic Games in the 400 hurdles in 2016. And he studied for a master's degree. As an athlete, he studied for a master's degree. He's a mechanical engineer, and his master's degree was in sports performance. And he built the first FAST technology that we developed for analysing sprint start. There's Dr. Richard Conway, who's a software engineer. Dr. Kevin Hayes is one of my colleagues from 20 years working together. He's a mathematician and statistician. And we added to the team Laura Ann Furlong, whose interest is in muscle mechanics. And then we have 3 other people, 2 of them are here. There's Matthieu, who designed the later plates that we used for measuring ground reaction force, hand reaction forces, and the detection algorithm. And Evan, who's going to tell you about his work in looking at the electromechanical delay that's part of this reaction time that we try to measure in the sprint start. So, can you just click the video, please? Just bring the mouse down, there should be a play button to the left. Okay. This is the most famous false start in athletics. This was the false start by Usain Bolt in Daegu in 2011, and it sparked my interest, together with some other events, in the false start. In this case, it was a very famous one, and there was no controversy over this false start. In fact, credit to Usain Bolt, he immediately realised he'd false started because he went even before the gun had gone. And I spoke to the starter who actually started that race sometime after it, and he said it was the easiest job he had to do because Usain Bolt was perfectly well behaved and accepting of the false start. What the starter and the officials team had to cope with was the reaction in the press and the media all around him to try and get him off the track without disrupting the event for the other athletes. And you can see he went even before the gun had actually sounded. That event stimulated my interest in the need to look at the start, because people started to say, well, was it Usain Bolt? And people were questioning the 100 millisecond minimum reaction time, and it's still being questioned. The thing about the sprint start is if you want to detect whether it's a false start or not, you have to realise that the gun will go and all athletes take a period of time to respond. There's controversy about how you measure that reaction, and secondly, what is that minimum reaction time? This is an ultra slow motion video of a sprint start. You'll hear the gun going, and then a fraction later, you'll see all the athletes responding. Gun goes now. See the delay? That was a legal false start, a legal start. Okay, and you can see the type of output that comes up here. You'll see that on the top, you've got the start line. That's the red line here. Then an orange line is the IAAF, or now it's World Athletics, minimum reaction time of 100 milliseconds. And then you can see the reaction times are measured on all of these outputs. The bit that's really interesting about these reactions are that you can see the graph for each one gradually goes up. And as you zoom in to get a precise measure of when did the reaction occur, well, it's kind of hard to actually detect that. You can look at it visually and say, oh, I can see where the graph began to increase, but it's actually quite difficult to define precisely that event without having some sort of variance threshold that causes a delay in detecting the event. In actual fact, if an athlete starts to vary the force before they then react, they may make the reaction time appear later than it actually is. So the response time sequence is set at 100 milliseconds. So why 100 milliseconds? It appears to be a really good number. Just think of it, 100 milliseconds is the human limit, not 99, not 101. They had to pick a number. And in actual fact, that number was arrived at in a very qualitative way. It's not entirely based in science. But we do know that there are delays that take place before a human being can react. The first delay would be the sound it takes to get to the ear. Okay, the time it takes for the sound to get to the ear. The speakers are usually placed right behind the athlete, and so it's usually a fixed amount of time of around 3 to 6 milliseconds. The time delay to get to the brainstem, about 10 milliseconds. Brainstem to muscles, about 50 to 70 milliseconds. And their time to muscle contraction after the muscle being activated would be about 6 milliseconds. And the appearance of an external force, in other words, the force that you would exert on the ground or on the blocks, would be about 15, maybe 20 milliseconds. Okay, there's a detection threshold delay. So if the blocks are instrumented to detect, like something like a 20 kilogram increase in force or a 200 Newton increase in force, there'll be a delay before the force ramps up to that point. That, according to this source, Bas van Hoorn, basically is about 110 to 147 milliseconds. So on the basis of that data, the athlete is given an advantage, that if they go in 101 milliseconds, they'll be okay, but that might actually, with this technology, be quicker than the human limit. There's other sources that say that the human being can react in less than 100 milliseconds. And there are athletes who will tell you they can do it. Therein lies the controversy. What is the human limit? What is the criteria we should have to disqualify somebody? Now just think about it. If you disqualify somebody on 100 milliseconds, on 99 milliseconds, what if the limit is actually 50 milliseconds? Then you will disqualify people who legally started. 120 milliseconds. Then the athlete may do a false start and get away with it and win the race because they false started, and another athlete who is maybe 200s behind that athlete will lose the race to somebody who effectively cheated or got away with it. The stakes in international athletics are huge. Millions of dollars are going to lie on the winner of the 100-metre final. Not just in winnings, but in the sponsorships. So the stakes are huge to get it right. In the evolution of this project, I started to question, what about this 100 millisecond rule? Is it fair or is it not? So we started to look at previous research. A really good thing for you to do, start by looking at previous research. And we found this paper by Komi and Ishikawa, which is actually a World Athletics or IAAF sponsored study. And it shows, as you can see up here, the onset of armed forces, the average is about 69 milliseconds. At the same time as that, the average for the block forces is actually 133 milliseconds. So on average, these are legal starts. It's an average legal start, but it's actually the hand reaction force is much shorter than the legal time. I looked at that and I thought, have we missed something? But there's only 7 participants. Do you want to make a rule based on 7 participants? Do you? I don't think that's a good thing to do. But the IAAF acted in the 100 milliseconds on a much more qualitative approach. And I started to ask myself, why did this happen? Why is it that the hand reaction force appears before the block reaction force? And is it really true that this happens all the time? That's where we really started. So our initial study was to put shimmer sensors, which are accelerometers, on the wrists on the head. And we also had another experiment where we put them in the forearms and upper arms. And we found that the shimmer sensors actually detected upper body movement, head movement and upper arm movement before the shimmer on the blocks. This was a very rough study, not publishable, but that was a starting point. These are the reactions times, or the reaction sequence over 48 starts by a number of athletes. You'll see that the hand force, or the shimmer in the hand, responded first every single time on every single start. Right? And we found that the head reacted second, and sometimes the shoulder and the elbow flipped. But here we've got a problem. The upper body is reacting clearly before anything else. That made us think Comey et al. Were right. Why did they not act on it? It was peculiar. So we now know from that little study, and we thought, when executing a sprint start, all athletes initiate the start with pushing the ground with their hands. That's what we hypothesised. The sequence of responses is quite predictable, but the timings between the events can vary. So you can't predict one from the other. That's what we wanted to investigate further. This push of the hands occurs before any force in the blocks. We then went to look at this 100 millisecond rule in practice, and we went and we published this paper on the effects of the rule changes and also a statistical analysis of the reaction times. Of 8,500 sprint starts, we used what's called an exponentially modified Gaussian distribution. So basically the distribution is steep, close to the reaction time, and tails off further away from the action time. And we looked at a probabilistic approach and tried to surmise where does the reaction time approach a limit. We found from that prediction probabilistic approach, we found that the reaction time limit for men was about 115 milliseconds, and for women it was about 119 milliseconds. A similar study was done by Lips et al., and they concluded 120 milliseconds was probably the limit with that technology that existed since the 1990s. So that's the approach we took. And that probabilistic approach, just recently, World Athletics asked me a simple question. What's this level of uncertainty that 99 milliseconds is a false start? Based on this data, 7 in 1 million chance that a 99 millisecond reaction is a false start. 7 in 1 million chance that it's a legal start. But that's based on a distribution. It doesn't mean that if you do 1 million starts, that 7 athletes will be able to do a start in 99 milliseconds. Probabilistic statistics basically gives you a confidence in your decision. It's not saying that 7 in 1 million will actually occur. It's an estimate from a smaller population to a larger population. So the motivation for our research was to make the sprint start fair for all athletes. It's not fair if 100 milliseconds is not the true limit. It's not fair if we can't measure the true reaction time. All these things are not fair. We need to get them right. To provide technology that supports the athletics officials in making their decision. They have to make a decision, but they need to have confidence in that. And to ensure objectivity in the decision on disqualification, to provide the strongest possible scientific support for the application of the World Athletics competition rules. And more recently, we are trying to provide information that's robust and can justify World Athletics decisions, and also revisions to the rules. So if they're going to change the rules, they need to have robust information to make those decisions to change the rules. The research programme was intended to map out the response sequence. And that was an academic project. That's how we started. The most important initial finding was that the first response tends to be in the hands. The movement of the athlete occurs after the increase in force. This is a well-established thing in science. Okay, so if you wait to measure or to detect the movement, they've already exerted their force on the ground or on the blocks. You won't see a false start. You actually see the change in force. You can't easily put EMG sensors on to look at the muscle responding. And even EMG is not easy to detect an event within a millisecond. It's just all the algorithms that are out there, very difficult to say. It started there. Okay. The challenge therefore is to detect a true first response, and that's a change in force, change in the external force. So this was our project, mapping out the kinetic sequence, and it involved, first of all, the sprint start response time measurement. How do we measure that response time? We needed to look at the mechanical delays. The muscle will activate, it will start to exert force, the tendon will lengthen before movement occurs. These delays are known to take place. But if you look at the literature, the values for that reaction time are controversial. We needed to start from scratch because we needed to get this measurement precise. Mechanical delays in sprint start response time need to be measured. And then we wanted to look at the hand and the block response times to confirm if or whether Comey and others were right. And we needed an event detection algorithm because it's one thing to see it in a graph, but how do you actually decide objectively the response occurred at this instant here and not another instant? And how do you do it like that? So that when it's detected before the athlete's gone down the track, that you're able to recall them back, give the information to the starter and say, we think that's a false start. It's more than likely to be a false start. So one of the other things we did, and Matthieu worked hard on this to get this paper together, to raise the issue and the awareness of the problems of the false start. We wrote a paper, a review paper, and published it in the Journal of Sports Medicine. And it had a number of key points. The validity and reliability of the sprint start technologies are questioned in the literature. We know that. If you look at the literature in depth, you find out that what IAAF or World Athletics are using is questionable. We know it's not ideal technology it's not really fit for purpose. The current 100 millisecond start limit may be rational, reasonable, but it's not supported by robust evidence. There's questions made about that. Some people think it's longer, some people think it's shorter than 100 milliseconds. Further research is needed to map out the event sequence during the sprint start and provide robust support for the rules. If you take a closer look at the sprint start, you'll see the threshold there and the curve going up. Yeah, there's a delay between the correct reaction time visually detected and when it's detected in a system. You can illustrate this with a schematic diagram. There's a sensitivity threshold there, and in these two graphs you can see there's a delay before the change in force occurs and the detection of the event. And you can see that depending on what that threshold is, you may find that some athletes will trigger earlier than others. Women are at a disadvantage because in general they're smaller and less able to generate the high forces. So they'll tend to react slower. In actual fact, I don't think they react slower. It's just that the rate of force development is slightly lower. And that explains the difference. There's also difficulties with the existing technologies. Look at this. There are 4 systems compared here by Stefan Willwacher. And he found that system 1 seems to give a set of values that are well clustered together. System 2 gives well clustered values, but it's later than all the others. Come to system 3 and system 4 later, but the same pattern of force was applied to the blocks in these systems, and you found that one system detects a later reaction time consistently than the others. If you're going to disqualify somebody in a precise rule of 100 milliseconds, but one system will let them away with it and another system won't, is that a good rule? I don't think so. And lots of people are not satisfied with that. There's a reliability problem. Look at system 4. Look at the number of outliers. This is supposed to be detecting the same events as system 1 and system 3. Yet there are variables that are sometimes up towards the system 2 values, and most of them are down near the system 2 and system 3 and system 1. The systems are obviously not named for good reason. So the thing is that the same pattern of force is applied many times, but the systems provide different levels of variation in the response time. You can't have that. So there's a reliability problem. We've got a validity problem, we've got a reliability problem with our measurement. What does that tell us? We need to do something about our measurement. Simple as that. The causes of the validity and reliability problems are illustrated in this graph. One is how you detect them automatically. There are different event detection algorithms in different systems validated by or approved by World Athletics. The developers of those systems are quite secretive almost about what that algorithm is. You have to do a lot of detective work to find out how they detect a response. Okay, so if they're using different algorithms and they're secretive about it, IAAF, World Athletics, have no control over how they detect the response. There are also different types of sensors. So we know there's sensors that are on, for example, the SACO blocks. They're force sensors, they're force transducers. And there's other sensors in other systems which are accelerometers. They give a different signal. Okay, and that would explain another reason why they give different reaction times. The athletes know it, they feel it, they think this system's too sensitive, this system's more liberal. They know it. So what we did is we built a hand plate, and our first effort was to put the hand plate into the track. So we built a track, and we put in the bottom right corner, you can see a picture of the hand plate looked like. It was a bit like what you would put in a long jump board. We fitted it in a track all around it. We built the force plate, and it was detecting vertical forces. This was Thomas Barr's first project, and he developed that prototype, and we tested it. And we compared the hand plate with an IAAF approved system, World Athletics approved system. So that was on the blocks. It was an accelerometer based system, Timetronics, and we started to do simultaneous measures of the IAAF approved system. We also put our own accelerometer on the rails as well. So we get 2 accelerometer systems on. We did that to check whether the technology of the Timetronics was fair. And we put the hand plate. And we did visual detection. And we found that the hand force on average was 74 milliseconds. The World Athletics approved block reaction time was 138 milliseconds. Okay, there's a difference of 64 milliseconds on average between them. Always the hands that appear to act first. There's quite a big standard deviation. That means you can't predict one from the other reliably. Okay. And the other thing that's not on here is our accelerometer, which cost about 15-20 euros, gave a comparison of about an average of 1 millisecond different from the World Athletics approved system. So our system that we built ourselves for 15 euros was able to mimic the approved system. This is what the output from the hand plate looked like. It went through a LabVIEW system, and basically you can see on the bottom left graph, you can see the shape of the signal. It tends to be flat on set, the gun goes, it stays flat, and then it begins to ramp up, and you can detect the event. The one on the right is showing when the gun occurred in a particular typical graph, the gun, the hands, the blocks. That was a typical event sequence. You can see at this point, we also started to put sensors in the blocks. These are force sensors rather than accelerometers. We went through, and this will be explained in detail by Matthieu, we went through various different designs because we didn't want to stick with the original plate because it was too big. It would have to be built into a track, and our idea was to make the plate low profile. And you can see here, the plate is now a bit like that. There's one for each hand, so the athlete can move it about to position that they want. There's a sensor with a marking where they put the thumb, and the gun goes, and you can detect the event. So the new low profile plate, which took about 5 or 6 iterations before we got to the new plate, the new low profile plate had to be validated against a force platform, a lab force platform. This kind of shows you what it looks like. It's quite close. So we became reasonably confident that that hand plate design was going to mimic what you would have in a force platform in a lab. Also, we have a event detection algorithm. Matthieu will talk in detail about that. It's a clever algorithm which mimics what the human brain would do to detect the increase in force. Okay, and in this case, you're getting values around 17 odd milliseconds. Evan is going to talk to you about measure of muscle activation. So we were able to look at muscle activation, and you can see in these graphs that the earliest reactions on the muscle responses are found in the shoulder, the deltoid muscles, and they activate before any of the lower limb muscles. And you can see that on the rear block compared with the front block. Okay, so you get leg actions from the rear block, and you get upper body actions detected here. And you can see that the arms actually respond in terms of muscle activity before that. We'll skip that. So we conclude the measured response times are affected by the technology used. The current sprint start information systems are not standardized because they've got different types of sensors, different types of event detection algorithms, and the same 100 millisecond rule applies. In the sprint start, the hand force appears before the block force, and the event detection methods can also be improved. Every millisecond of error represents in a race, an international race, a distance of 1 centimetre. So if you have a 10 millisecond error, that's 10 centimetres. Let me tell you, if it's 100th of a second, which is the limit in time that you would usually measure to in a race, it's 10 centimetres. If I'm standing on the line watching a race, I can see the difference of 100th of a second. I can say, you're first, you're second. I can tell it. Dead easy, because you can see it. Changes in technology and rules will have to be made in order to make the sprint start fair. That's one of our conclusions. So I'm now going to finish off by talking about changes in policy. Where do we start? Change in policy by publishing your findings. Be thorough, be systematic, put a structure in place for a big project like we've had to do, and publish your data. It took us years to get to the point we're at now. We're still not where we want to be. Okay, we patented, we got 4 patents on the technology as well. the university that I worked for wanted that protection in case it becomes something that companies want to use. So how did we influence technology? Our initial exploratory work was done with inertial sensors. Statistical analysis study was done. You saw that one about looking at the 8,500 starts. We developed the first hand plate. That was a proof of concept. We made our first patents in 2017 and were published in 2019. It takes that long to get a patent to be fully published. We presented our first findings on the big plate. We presented them. I asked to talk to the IAAF Technical Committee, and I did a presentation. It was done by video conference in 2018. The response was, it was okay. It wasn't negative. It was, well, we've actually spent a lot of money in Sprint Start, and you're telling us we're going about it the wrong way. Imagine that. They had spent a lot of money getting somebody to design new types of blocks. And I was coming along and saying, well, you can do all you want with blocks, but you're not going to get first response. And here's the reason. That was a really tough one for them to take. So they wouldn't fund us. We then presented again in 2019 with an updated version. 2020 through 2021, COVID restrictions affected our work, affected everybody's work. Matthew worked away on that, and we continued to develop the low-profile plate. And eventually, we've got a US patent which covers the whole world now, between the earlier ones and this. And then 2022, we got some lucky breaks. We've been waiting for those breaks for a while. Devin Allen, it's not so much lucky for him, but he false started in terms of the rules. And there was uproar. I was in the stadium when this was going on. Devin Allen was a local man. He was training in Oregon, and he was competing in his home track in the World Championships. I think it was the semi-final, 100 metres. He get disqualified for a 99 millisecond start. If you look at the video of it, you can't see it. You can't say, oh, you can see he moved first. But remember, your first response is not movement. The first response is force increase. I was then asked, the world press got on to me. They got on to you as well, Matthew, didn't they? I was asked the question, do you think he false started? And I basically said, there's lots of questions about it, and gave them the sort of party line. But I said that our paper on that technology would suggest that the limit is somewhere around 115 milliseconds on that technology. But there's other technology that would find they could go a good bit quicker than 100 milliseconds. So I told them that. That was followed up in October in 2022 because we invited Seb Cole to come to our university, and we provided them a live demonstration. I wonder if we could go to that link, please, and move it to about 2 minutes. Yeah, that's fine if you could play it.
Nation. A big chunk of it was about teacher training, physical education.
So you'll see the video of
applied
this.
to that. Both universities came about roughly the same time. And I love the fact that the focus is on world-class sports science. And that's what our sport is. I'm just delighted that I had the opportunity to see that.
Sport is so important in so many ways.
So Seb saw it, and seeing is believing. We had the system there. We had something like 4 international athletes. The start sound went, and before they'd get down the end of the track, Matthew had got the response times up on the big screen. You saw the big screen there. So you saw the athlete starting, you saw Thomas Barr starting there. Before they'd gone halfway down a 20-metre track, you could actually see, here's his reaction times for all of the parts, you know, the rear block, the front block, the hand, right hand, the left hand, and the accelerometer. And it was automatically detected. and they were always shown quicker than 100 milliseconds, weren't they? So he saw that this rule does not apply to hand reaction times. That was a big break for us. We're still working with them. And so if you want to change policy, you've got to get the information to the right people. We were fortunate that in Ireland, the head of world competition is basically an Irishman. He's an Irish official. And I know him personally, I've known him since he was an athlete. And I think the other thing that's quite important is we've got to try and influence people and use every avenue to do that. I think it did help, the fact that I was a coach. You know, it did help. But scientists need to get into the people who will influence change. And I do know that World Athletics are taking the issue very seriously. But we're not able to give them the full product that's fully automatic. We've got a wee bit more work to do. We need to make this system run on 8 sets of blocks. We need to make it work in real time. And we need a timing company to be able to come in and say, yeah, we'll do this. We also need World Athletics to be prepared to change the rules. Seb Coe's response is, I want the rules to be fair. I do believe he's absolutely genuine. And so we just need to keep working on saying this can be done in a fairer way. But there's no point in coming in with a change of rules on a system that's not fully tested. It will take years for this type of approach to be adopted because it will need to run concurrently with the existing system for about a year and then become integrated to a rule change. Put up there the final comment, the genie is out of the bottle. That's a sort of British saying, and it basically means you can't put it back in, the secret is out, and you can't put it back in. But we needed to get to that point that the secret is out. And the secret is now out amongst athletes. They now all know that the measurement in the blocks is kind of not ideal in terms of providing a reaction time. I'm now going to be handing over to Evan and to Matthew. Okay. Thanks.
Hi everyone, my name is Evan Crotty. Unfortunately, I don't have as good an accent, a Scottish accent as Drew. From Ireland, my PhD in Ireland. Irish people are known to talk very fast, and Matthieu has me warned to keep it nice and slow. Did my sports science degree in Ireland in the University of Limerick. Moved on to the PhD as part of the FAST project, and now I am still in Limerick, so I love Limerick. I'm lecturing there at the minute. So what I'm going to discuss today is firstly, my part I played in the FAST project looked at mapping the response sequence experimentally, and then I'll move more towards the practical application that we looked at in PhD, where we compared plantar flexor performance in sprinters and physically active people to see if there's any training influence. So, as Drew mentioned, FAST project stands for Feasibility Analysis of Sprint Start Technologies, with overarching aim to map out the kinetic sequence of events during sprint start. So for the first part of the presentation, I'm going to discuss my side, which was the influence of mechanical delays on sprint start response time. So again, first part of the presentation, I'm going to discuss how we mapped out, firstly, the response sequence experimentally, and how we also looked at those mechanical delay periods. So, as Drew mentioned, there's a sequence of events that occur before an athlete produces a sprint start response time. You have the gun going, a delay between the gun and the signal being picked up by the ear. From the ear through to the brain, another delay. Brain through the nervous system to this dodgy looking muscle activating, and muscle activating then to force output or movement onset. And this delay period between your muscle activating and force onset or movement is called electromechanical delay. As Drew mentioned, there's been previous papers that have estimated what this delay period might be, maybe 5 to 10 milliseconds. There has been no study that kind of looked at it experimentally in the sprint start. So that was one of my goals for the PhD. We focused on the plantar flexor muscle tendon unit. So just some quick anatomy on that. You have your obviously Achilles tendon, which connects to your gastroc and soleus muscles. Function of the plantar flexor muscle tendon unit is to plantar flex and dorsiflex the ankle joint. In terms of why study the ankle joint and plantar flexor muscle tendon unit, firstly, research has shown that it explains about 23% of the variance in your normalized average horizontal external power from the blocks. Second reason is obviously your ankle joint is in contact with the blocks, so more proximally generated forces are going to be applied through the ankle joint, which is important then for a discussion on sprint start response time. So, in terms of my research objectives for the PhD, we had two main things I looked at. Firstly, was to establish that muscle sequence of activation, what order do the muscles activate during the sprint start? And secondly, to examine the mechanical delay periods. So, our first experiment conducted was more a preliminary investigation. We had a group of sprinters come in, sit down in a chair, put their heel basically on this little white little thing on the ground there. Basically, they lift their heel as fast as they can. You can see we had EMGs attached to the calf muscles, and basically from that we got an estimate of electromechanical delay. Second thing they did for us was they did sprint starts in a competition environment, and we measured sprint start response time from, you can see it there, with an accelerometer attached to the blocks. So this is our first experiment to see was there a relationship or potential relationship between electromechanical delay, this delay period, and sprint start response time. I found that there was a moderate correlation between the two, so that kind of required further investigation and to move more towards a more ecologically valid experiment, which we did. Myself and Matthieu, COVID delayed us a small bit, we got the experiment done, so I moved on to testing this in our lab, where we had, you can see the hand plates here on the right, we had sprinters in blocks, force data coming out of the blocks. They had EMGs attached to 8 major muscles, so 16 in total, 8 each side. And we got sprint start response time as well from the accelerometer. So that was our setup in the lab. So we had 15 sprinters who are of national or international level who completed the trials for us. In terms of our analysis, we looked at muscle activation onsets, our ankle joint kinematics, we got force onset or increase from the set position from the blocks, and we got sprint start response time. And from that, we're able to estimate our mechanical delay periods, which I'll come back to in a slide or two. So Drew kind of presented this a bit earlier. What we looked at is if you have on the x-axis here, 0 being when the gun went off, any time after that is going to be your time relative to the start signal. So we looked at, on a group level, what muscles activated first. So we're going to look at the front block side first. So that's the far side of the athlete. So I saw firstly, at a group level, the deltoid muscle or shoulder muscle was the first to activate. Following that, you have your rectus femoris muscle of the quad. And the third muscle to activate was tibialis anterior. Go to the rear block, we saw exact same thing. You had deltoid or shoulder muscle activating first, rectus femoris again, and your tibialis anterior, which all kinds of aligns with shoulder propulsion, your knee flexion, hip extension, and your ankle dorsiflexion, kind of initial push movements in the blocks. What was really important for this is that we saw, firstly, that the shoulder or the upper body muscles activated before any lower body muscles, and it also did it in less than 100 milliseconds. You can see there it's about 65 milliseconds. We saw deltoid muscle activated, which is significantly less than the 100 millisecond rule, which we was discussing. So again, the main objective of this research was also to provide a numerical figure towards that delay period, the electromechanical delay I presented at the start, which was estimated to be 5 to 10 milliseconds in that paper by Comey in 2009. So what I presented is the delay periods for the front block and the rear block as average values, but obviously what's important is the limit or the lowest possible value that we could observe. So what we saw for the rear block was that this mechanical delay period could be as low as 7 milliseconds. So that was definitely within the range of what they proposed by Comey et al. It was good to actually get a solid figure as to what potentially this delay period could contribute to your sprint set response time. So that's kind of my part in the FAST project, I presume, looking at the mechanical delay periods and also looking at the onsets and the order of onsets. Another kind of more practical thing I looked in the PhD, which I'm going to discuss now for the next 5 minutes, is we looked at plantar flexor neuromuscular performance, and we compared a group of sprinters to just physically active individuals to see if there's any differences as a result of their training background. So when we talk about neuromuscular performance in any muscle tendon unit, there's a number of components that contribute. So you have your mechanical components, such as your muscle tendon unit stiffness. You have neural components, such as your neural drive, which we measure with your EMG. And you have factors such as morphological, such as your fiber composition, and your evoked contractile twitch, which can be measured basically shocking the muscle, and your muscle size as well. So certain variables we look at, electromechanical delay is kind of in the middle of your mechanical and neural side, and maximum muscle strength is in between your neural and morphological side. So what we did is we're obviously comparing the plantar flexor muscle tendon unit. We had two groups. Our first group were explosive power athletes, or sprinters in this case, 14 athletes with 7 males and 7 females. And we compared them then to physically active participants. Again, we had 14 athletes, 7 males and 7 females. The reason we picked this group to compare them with is we could have compared them with endurance athletes, but even looking at the recent Olympics or the times from, say, the top 800 meter athletes in the world, we know that they have an element of speed training in their training. So if we really want to compare the speed training related background and the neuromuscular performance, physically active participants were our best bet. So in terms of our method, we had 2 main contractions that all of them performed. Both of these were isometric in the isokinetic dynamometer, and we measured this across 3 different ankle joint angles. So we had 10 degrees plantar flexion on the left, 0 degrees or neutral, and 10 degrees dorsiflexion on the right. The reason we picked these angles is because in the first kind of 100-150 milliseconds of the block push, these are kind of the angles that the joint tends to go through. So that's why we went for those 3 angles. And we got both our participants perform explosive and maximal contractions across the 3 joint angles. So I'm going to discuss 3 main variables that we looked at. We looked at plantar flexor maximal strength, we looked at rate of force development or rate of torque development, and then I'll discuss tendon stiffness and muscle size that we looked at the end. So we normalized all our maximal strength values to body mass, and what we found was at the plantar flexion angle, there is no significant difference in maximal strength between your physically active and your sprinters. Same thing for the neutral angle, no significant difference. But for the dorsiflexion angle, we saw that sprinters had a significantly higher maximal strength. So we started the question then, what was the reason for this, that sprinters had a greater maximal strength at this particular angle? And we came to a main conclusion that it's related to the muscular demands placed on a sprinter. So if you see, the first 30% of stance when the athlete comes out of the blocks is ankle dorsiflexion. You see as she lands here, ankle dorsiflexes there. before plantar flexing. What we suggested is potentially because there's such a high amount of rotational joint moments when they land there, athletes tend to try to reduce that dorsiflexion range, and that might be the reason that they have greater maximum strength at the dorsiflexion angle. So that's our potential explanation for that. So maybe sprinters, as a result of sprinting for many years, have developed this requirement for large plantar flexion moments at that dorsiflexion on touchdown. Second thing we looked at between the sprinters and physically active was the rate of torque development. So if you think of your torque development curve, we looked at 0 to 50 milliseconds, 50 to 100, and 100 to 150 milliseconds. What we observed were sprinters had higher rate of torque development in the first 50 milliseconds across all 3 joint angles. And if we look at the research, they say that 0 to 50 milliseconds is mainly determined by your muscle activation, okay? And research has also shown that sprinters' explosive type training increases this muscle activation through increased motor unit discharge rate. So that's a potential explanation for that early phase rate of torque development difference between the two groups. Again, for 50 to 100 milliseconds, we saw sprinters had significantly greater rate of torque development across the 3 angles. But for 100 to 150, there is no significant difference across the 3 angles between both groups. Potential explanation for this, we saw, if I go back to the slides, 2 slides ago, we saw for your plantar flexion angle, your anatomical 0, there is no difference in the maximal strength capacity of the muscle. So that might explain why there is similar difference or no difference between the 2 groups at that 100 to 150 millisecond point. So we measured loads of variables, but the last 2 I'm going to look at are our tendon stiffness, which we measured attached to ultrasound to the back of the calf. You can see this video here. That's basically left of the image is going to be the very back of your calf here. Right of the image is going to be towards the front of your tibia. So what we did was measure, see that little white branch there, that's your tendon, muscle tendon junction between your medial gastroc and your lateral gastroc. We measured that elongation using the ultrasound attached to the back of the calf, and we measured torque increase also in the dynamometer to get an estimate of tendon stiffness. So we observed no differences between sprinters and physically active for this variable. We can see there's also very high levels of variability with tendon stiffness. Second morphological property we looked at was muscle size. Again, ultrasound attached to the back of the calf. We measured medial gastroc muscle size, which is a good correlate of muscle volume. So we just did this to see was there any significant differences between the 2 groups in terms of their calf muscle size. Again, we saw no differences between the 2 groups, so we kind of said that the differences between the groups in maximal strength or rate of torque development were not down to the morphological properties that we examined in our study. In terms of the practical implications of that investigation, what we saw was potentially sprint-specific training induces improvements in your early phase rate of force development across your muscle tendon unit lengths. As with any study, you have to recognize the limitations. The first one being that this was just a cross-sectional investigation. We brought the sprinters in, we measured the rate of torque development, their maximum muscle strength, but we were not training them. This was not a training study. It's very hard to control sprinters and their training, so this is just bring them in, measure them, send them away again. Second thing that we have to look at is also genetic influence. So we obviously don't know the genetics of both the groups. Obviously we know this has an influence on muscle properties, on your muscle fibers, etc. So that is the second limitation that we have to recognize also. That's kind of my 2 main areas of research I looked at in terms of PhD. So I have the side of the FAST project, looking at the response sequence and looking at this practical study. Last bit I kind of wanted to finish on was the importance of upskilling and collaboration. So obviously throughout those studies for the PhD there was a lot of skills that needed to be learned and implemented. We had EMG, dynamometry, motion capture, ultrasound and MATLAB. As first year I was completely lost as to how I was going to learn all of these skills. actually went to the first conference, ISBS in New Zealand, and my supervisor Drew, who supervised Laura and Furlong, who was at that conference, actually took me under her wing. Brought me to Loughborough University, where I upskilled in motion capture, ultrasound and MATLAB. So I bring these skills back to Limerick, try and implement these to do my tests and research. While I was there, I tried to do a bit of training myself, didn't get much done. More training in the lab than training on the track. But it was really, really productive in terms of collaboration, to hash out what my studies would look like, to upskill in the areas I need to upskill in, and to create connections. Decided to myself, Matthieu, being able to complete PhD research during the time of COVID. Wasn't the easiest time to collect data, but we got there in the end. After long, 4.5 years, Laura and Furlong, there at graduation last year, who helped collaborate with Drew, obviously as a supervisor as well. I think my takeaway message from this is research is hard by yourself, collaboration is good, chat to people, try and upskill as much as you can. There's loads of people even in ISBS, there's loads of networks, just help each other, share ideas. I think that's the most important thing I learned throughout my PhD. That's it for me. Thanks very much.
So, as Drew, I think I will try to do something as Drew did, not to go too much into science, but just to tell you the story and what it takes to try to develop something new, because it's what I try to do, to develop a new start information system from zero. And it was kind of hard, but I think it's a good way for you, especially the students from DIGISPORT, for example, that maybe in the future will have to build something new. And even for people who are more in coaching practice, more in the ground field, it could be interesting for you to understand what it takes, and when you used a system to measure something, to see what it takes to develop it, and also to see that in all systems there is some limitation, and if you want to be a good coach, you need to know the limitation of the system that you used. But before to go in the presentation, I would just want to tell you a little bit about my story, because my story could be your story. Like, as you can hear, I'm French. For sure, maybe a little too more French, but anyway, I'm French. I come from Grenoble, and I came to Rennes in 2014 because I was accepted at the ENS Rennes. And in 2015, I was like you today. I was a first-year master here. At this stage, it was not called EOPS, it was called M2S, but anyway, I was at your place. And during my training, I had to do an internship abroad. So I went to Limerick the first time in the summer of 2015. Here, I was more about biomechanics, but in cycling. And when I had to choose an internship abroad, I wanted to discover a new sport. So, and apply biomechanics in another sport, because as Evan said, it's always good to try to see new stuff and to try to, by applying biomechanics in another field, to build some skills that I didn't have at this stage. So I went to Limerick and I did an internship with Drew. And at the end of the internship, it's the first time that maybe we speak about a PhD project. So to come later in Limerick to do my PhD. And for me, it was, I never think about this. I think they can also tell you this, but when I came, my English level was very, very bad. I was not able to understand what they said. and for me it was very hard to speak, but anyway, so it put me this idea of doing a PhD abroad in my mind, and I said, oh yeah, it could be a good opportunity, but at this stage it was just like something very surprising and just an opportunity. So after passing the aggregation the year after, I went back to Limerick, for this time for a voluntary internship to show to the founders that I was very interested about the project and I really want to do a PhD in Limerick. So during my second year of master, I was again at your place. I was it was the first year of the master EOPS, and I did my master here. So I applied for funding in Ireland, and I get it. So I spent the last 4 years in Ireland to do my PhD in full time with money from Ireland. And unfortunately, there is a little pandemic that happened, so it impacted a lot my timeline, and it was very hard to test athletes and everything. So I'm still doing my PhD. This year I came back to France because I had to come back. And fortunately, I got a job of ATR at the ENS Rennes. And with all the teaching, I tried to complete my PhD. I didn't do too much this year, but I will have a very busy summer to finish it in 2023. And if I said this to you, if I tell you a little bit my story, it's because if Drew is here and Hugo works a lot for these two, there will be Erasmus project. It's done or it will be done.
Okay.
So there is a strong link that we hope it will that we will bring between Limerick and Rennes. And if you are interested about sprint, but there is not just sprints in Limerick. There is like psychology, PE. There is also a new department about gaming. So gaming, but in the performance part. So there is a lot of opportunity. And if I was able to go in Ireland, definitively you can do it. So now I will tell you the story about what we try to do in the FAST project to propose something new, a new start information system which is more fair for the athletes, meaning that it's more accurate to record the reaction time. As Drew said, there is two ways to improve the start information system. First is to develop a new system which is able to record the onset of arm force reactions, so not using what's happened on the feet because it reacts too late, but what's happened with the hands on the floor. And the second way is to improve the event detection algorithm. So this will be my two parts of this presentation. The first part will be what we do to develop a new hardware system to record the hand force reaction, and the second, more about the software, what we do to implement a new event detection algorithm, which is able to run in real time to be used in competition. When you try to develop something new, there is some methodologies that you have to do, that you have to choose. There is two main ways that you can do when you try to develop a start information system. So as Will Washer do and as the World Athletics do to certify their start information system, they built a robot that mimic a force pattern that can be applied on the block, and with this force pattern they can compare different starting blocks and see the difference in performance. So what is good with this kind of method that it's very reliable. You always apply the same pattern of force and it's easy to compare different systems. And you can also control the movement pattern if you want. If you can try to increase more the forces, to increase the rate of force development and see what happens in terms of reaction time. So you can control the movement parameters. But the main disadvantage of this is that you don't take in consideration the variability and the diversity of human movements. When we bring subject, even if it's the same subject and this subject did 6 starts, the 6 force signal will be, we are not the same. there is some variability. And it's not because your system works with one pattern of force that it will work for another pattern of force. So to be able to have one solution that fits for everyone, you need to understand this variability. So it's for this reason that we decided to use a more ecological method by using by using subject and bringing some sprinters in the lab. So with this, by testing sprinters, if we test a lot of sprinters, we have a good idea about the complexity of the human movement. Each subject will be different, each subject will apply the same pattern of force, and if the solutions that we develop work for all our subjects, we have a good chance that it's work for everyone. However, we don't control the movement parameters. So if it works for one subject and the solution didn't work for another subject, we don't really know why. We need to find some hypotheses and try to change our systems to be able to try to find a solution, but without knowing too much why it's not working. And for this, to have a good idea about the variability of the movement, we need to test a lot of subjects with different height, different span, different size, everything. So this, it takes longer time than just to build a robot and change some parameters. And when you try to develop something new too, you have to be able to know if what you measure is good or not. And for this, you have to find a system where you know that is working well, it's your gold standard, it's your reference, and you can compare it. You can compare your results with this system to be able to say, oh, this measure, it's close, so it's good. So you have to define a gold standard. For example, there is a new area, it's markerless motion capture, and it's developing a lot. And if you want to know if your system is good for different sporting tasks, you have to compare it with the gold standard, which is the motion capture with marker. So by comparing the results of the gold standard, you are able to see if your system is good or not. So it's this methodology that you did to develop our new start information system and the new algorithm. So now I will tell you the story about the development of the prototype to assess reaction time from the ENS force reaction. So at the beginning, as Drew said, we built a big plate, so it's Thomas bar. I will not present it to you because Drew did it. That built this big plate. So what was good with this plate is that we can measure on reaction time in the ecological way directly on the lab. So the sprinters can go to the lab, they use their own spikes, and they can do real starts, okay? And it was not possible to do it with the force plate in the lab in Ireland, so it was a good this plate allow us to testing in the real condition sprinters. And it also helped us to assess the precision of the prototypes that we developed, because we can put our prototype directly on the top of this plate to be able to compare it for the same trials. But as Drew said, this plate was very big, very heavy, and if we want to use it on the field, that is the main purpose of what we try to do, we have to dig a hole in every stadium, and it's definitively not possible. So we try to develop a system that works as a force plate, but low profile. So at the beginning, we built the first generation of prototypes. So it was kind of easy solution. We just used a blade of steel first and aluminum then because it was lighter. And on this blade, about 1 meter, we just stick some strain gauges. And the strain gauges so it's not the force that measures it, it's the strain. But when you apply force, you deform the blade, and this deformation is recorded by the strain gauges. and is as a load cell. So here you can see it's an example that we get from one of these first prototype. So the black line is the force plate built by Thomas, and in the gray line you have data from the prototype, and by this we can compare the two results. And here you can, and the dashed line represents the reaction time. And in this example, you can find that there is a good agreement to detect the reaction time from both devices. So we were happy about this, and this means that strain gauges can be used to assess end reaction time. Unfortunately, like I said, it's not because it works for one trial with human variability that it will work for every trial. And with this first generation of prototypes, we didn't get some very consistent results. It was working well in some times for some trials, and for some others, it was not working at all. Like here, as you can see a clear push record from the load cell, but from the big plate, but not from the prototype. So we get a problem with the variability of movement. So to try to improve it, each time we bring one or two subjects in the lab, we do some testing, we see what was not working well, and after we try to modify the prototype to try to improve the accuracy. So we did a couple of circles like this: pilot study, modification, pilot study, modification. We try to use to increase the number of strain gauges. We try to use different sizes of strain gauges, different kind of strain gauges, but at the end, we get the same problem. In most of the trials, we get a good result, but in some trials, the prototype didn't work well, so it was not good enough. We need to have a solution that works in every cases for every trials. And like I said, we don't really know each time, because we can't control the parameter, what is work and why it's not working. But with all this experimentation, we made some hypotheses, and we conclude that to be accurate, the strain gauges had to be directly put under the point of the force application. If the pressures that you apply in the end is too far from the sensor, you miss some results, you miss some part of the curve, and you don't have the results that you want. So we built a second generation of prototype with small plate where we can manage where the sprinters can the sprinter can manage where he put the plates according to his own preferences to be able to manage the point of application of the force and the location of the sensors. So we built some small plates. Again, we use the strain gauges, and on the prototype, you make a small target, and on this target, it was asked to the sprinters to put his thumb directly on the target. And in this way, we can manage that the thumb is just below the strain gauges. And then we test it. The first time, we just create one plate for the right end, and the small pilot study was good. We get good agreement, especially for the reaction time. It was nearly perfect. So we were happy about this, and we decided to increase the number of subjects. And for some subjects, we were very happy about this. We get very good agreements, and it shows that, oh yeah, we have a good prototype. But each time, it's just working for the majority of people, and just for some people, it was not working well. And each time, you feel very great, and after, when you see it's not working, you feel bad. So emotionally, it was like this PhD. And this time, we were thinking a lot to try to understand what it was not working, but this time we not question the functioning of the prototype, but more the experimental setup. In fact, as I said at the beginning, we just built a prototype that were able to record the force for the right end. And the big plate, there is just one load cell in the middle of the plate. So it means that the signals that you get from the whole plate, it's the sum of the two pushing actions from both ends. But visually, we can see that some athletes, they push in kind of symmetrical way. They push on the floor to lift themselves, but some others, they don't push symmetrically. There is one push with one hand, and the second is more sliding like this. So this time is the experimental setup which was not adapted to validate the prototype. So we designed a new setup which were able to validate the prototype. This time we had to change a little, and like I said, in the lab, it's not possible with the configuration of the force plate to test both ends in the same time. But we did one comparison in the lab using separately right ends and left ends to be able to record the plate from the force plate on the lab and on the prototype to validate if it was working well or not. And we also do one validation study on the track. So on the lab, we were able, again, to compare it with a very good gold standard, the real force plate on the lab, and we get a very good agreement. And this validates that it was like, I think, 10 subjects that did the experimentation. It was not too much, but at least this time it was working well for 10 subjects. And we also went on the track for both reasons. Try first to record in the same time both ends, because this time we built also a prototype for the second end. And we were able to see that, yes, for some trials, there is some people that don't push symmetrically in the same time. So it means that to record the response time from the ends, you have to use both ends and detect which ends react first. And it's also, with this, we were able also to test the practicality of using this kind of system directly on the track. And we were confident enough to bring Sepco, and we did a presentation in real time with Sepco, with our system, to say, oh, we have a system that nearly works in real time. So in conclusion, for this hardware development part, we had to do numerous experimentation to develop a technological solution to assess the reaction time from the ends. We had, in the middle of our journey for this, to change the experimental setup because we found that it was not adapted to validate the prototype. And it's also prove all the work that we done and all the small pilot studies that we done, that to be able to provide a good solution, you have to work with humans, you have to work with sprinters to deal with the human variability and to be sure that the system that we develop works in every case. Now I will also tell you a bit the stories that we did to develop a more precise event detection algorithm. Drew gave you some examples. There is a lot in the literature, not too much about sprint start, but in the literature about event detection algorithms, there is a different event detection algorithms, and they provide different results. And it could be wrong, you know. If, for example, you track when you in the coaching practice, you track the power of your athlete, so you use RFD. But there is a lot of paper about this that show to detect the beginning of the increasing that you will use to compute the RFD, that there is a substantial effect of the algorithms that you used on the outcome, the value of the RFD. So if you don't know this, and you are not aware too much, and you change the system to track the RFD, you will, in the middle of your coaching career, and you will not find the same results. It's not because the training effect that you did with your sprinters, it's just because of the technologies. And as Drew says, the threshold methods that we think that it are used by the current system, they were wrong because they not deal too much with the variation, with the different quality of power of different sprinters, and they induce a delay to detect the reaction. So we try to fix it. So the main challenge to deal with the signal is to try to deal with the variation prior to the onset of force, because this variation will impair the algorithm functioning, and it's for this reason that they used, to avoid this problem, a big threshold to not trigger the start information system too soon, but to more your threshold is high, more you induce a delay, and less you record a real reaction time. So again, like I said, we need to define something to be able to compare our results to see if our algorithm is good or not. And in the event detection, the gold standard, according to the literature, is the visual detection. It's your eyes is able to deal with the variation and to able to see, despite the variation, the beginning of the onset is here. But when I try to develop my algorithm, so first I had the dataset, and two experimenters assess visually the beginning of the onset of force. And when I check the results, I see that there is a difference between the two experimenters. This is a Bland and Allman plot. I don't know if you know this, but they plot the mean of the reaction time given by the two experimentators against the difference between the two experimenters. And you get the amplitude of the limit of agreement, give you a good idea about the level of uncertainty of the measure. And here, the visual detection in the dataset has a level of precision of around 30 milliseconds. But, I just said that visual detection is the gold standard. So if the gold standard has a 30-minute precision, it's very weird because World Athletics claim to have a precision of 1 millisecond. As Drew said, Devon Allen was disqualified for false start for a reaction time about 99 milliseconds. He was just below 1 millisecond of the threshold, and he was disqualified. But here, the gold standard has a level of uncertainty of 13 milliseconds. Maybe it's us that didn't assess the reaction time visually correctly. But if we compare with the literature, here, the amplitude of the limit of agreement are around 90 milliseconds, 3 times more than us. So it validates our data, like what we do, it's soon okay, according to this study. And I try to go deeper in this problem of gold standard and try to see if we can improve the visual detection. So we use different size of windows to display the signal to assess the reaction time. We try to use different software too. So I try different parameters and try to see the influence of these parameters on the visual detection. And each time I have approximately the same level of precision of 30 milliseconds in sprint start. So the conclusion of this work was that the precision of 1 millisecond claimed by World Athletics soon unrealistic. And the gold standard soon to have a level of uncertainty of 30 milliseconds, which seems very high. So maybe a more objective method can do better. And it's what I try to do, to provide a better solution than the gold standard finally. So I test different versions of the algorithm, and each time I try to improve it and to have a more consistent results in all the data sets that we get about sprinters that we test before. And the final version of the algorithm gives an amplitude of the limit of argument, which is smaller when I compare with the both experimentators than when the amplitude of argument of 30 milliseconds of the two experimenters. So here, it means that the algorithm gives a more consistent results than the visual detection. So we are quite happy about this. And what the Blandet-Allman show plot to, that there is a systematic bias. It's meaning that our algorithm gave a reaction time around 8 milliseconds quicker in average than the visual reaction time. But for me, this is not a problem, because when I check and I go deep in some results, in some case, visual detection is definitively wrong for me. For example, in this tutorial, in the black line, you have the max snap. The max of snap, it's it's kind of the acceleration when you are in the movement. So it's the second derivative of the first signal. And here the max of snap occurs before the visual reaction time. But to reach the max of snap, you mean that you have produced some force before. So if the max of snap occurs before, it means that definitively it's not possible to reach it instantaneously. So the visual detection provides too late detection. So here, it seems that the gold standard is not a gold standard. And I'm pretty happy, and after it's hard to prove, because I don't have anything to compare, but what I have to prove now is to say that what I get is better than the gold standard. To not use the gold standard to validate my study, but to say what we get is better. So this is the algorithm functioning. I will not explain it because it will take too much time and I already speak too much. But I will just show you quickly how it works. So he defined first the search interval where we know mathematically the reaction time could be. Then he defined according what happened prior to the force onset, the variation. I use the variation to be able to define different options for the reaction time. And then the algorithm will just select the option that failed into this search interval, and then he finds the best compromise to define the reaction time according to this option. And with this, I have algorithm, as you can see here, that don't provide a delay. And I will have to prove that works better than visual detection, because it's more objective. So in conclusion, numerous versions of the algorithm were tested to find the best solution possible. Again, it was kind of the same story than for the force plate developments. The first version of the algorithm working well in 90% of the cases, but for 10% not. So then I had to change it, and it was working well for 95% of the cases. And again, I tried to improve it to be able to work in every case possible. So we had to do a lot of testing to be able to provide a final solution. The extended testing that we made gave information about the precision of the gold standard in event detection, and the precision of the visual detection is around 30 milliseconds in sprint start, which is much bigger than the 1 millisecond start information precision claimed by World Athletics. And knowing this level of agreement maybe can be integrated in the regulation to have a more fair regulation, because definitively 1 millisecond precision is currently not possible. And we developed an algorithm showing promising results, and hopefully what we want to do is that it becomes the new gold standard in the future, not just in print start, but also in a different branch of biomechanics, for example, to compute RFV. So currently I test I just did recently test the algorithm in the isometric mid-type pool data and show that my algorithm provides better results than what is currently used to assess the RFD on the isometric mid-type pool. The final conclusion of all this work is that to be able to develop a measurement system which will be able to deal with the human variability, it's something that is not easy, that takes a lot of time, but you need to dedicate a lot of time to be able to find a unique solution that works for everyone. There is, as Evan said, a necessity to work in a team with people with different skills and from different areas, and maybe in the future in different countries too, to be able to deal with this kind of problem. And what you can get, for sure that it will help you in the future, even if you don't work in the sprint start or in sprints, that it's to know that each system measurement has its own level of precision. And a good researcher or coach has to know this level of precision when using this kind of system. And to finish, if one day you watch on TV that reaction time is recorded by ENS, you will remember that this change was initiated by the FAST project team from the University of Limerick. Thank you.
So thank you very much. We'll give our presenters a couple minutes to slow down, and that's going to give you time to think of your questions. So thank you very much, because I really love how you showcased, you showed us something that we're trying to tell students all the time. Everything starts with a good question, with a good story. And that was excellent. That it's proof that you start with a good story and you don't stop until it starts to make sense for the applied question. It's not because you started to do something, it's like, good enough, I've done my part. No, it's like you keep refining and refining and refining until you end up with something that is actually doing what you intended to do in the first place. So that was most excellent. Thank you very much. As Matthieu mentioned, we have Erasmus links with the Limerick, and we've had for some time. But you can also see how important it is for students like Matthieu, who started from here and who create a bridge or strengthen the bridge. They go abroad, they take their bag, and they go and they study abroad and in another language, in another country, and they find good people. And there's people who do good science in a lot of places, and that's a really good example. So that then when you come back, now we really want to keep that collaboration going. It's extremely valuable for us. And Limerick is now a huge interest for us to develop. There's a really strong bridge, and we'd like for more students to be interested in that. And we'd like for students in Limerick to be interested in us as well. Because I think, as you've seen, I mean, it's not different. It's not that much different to what we're telling you all year long, is that basically everything you do has to make sense for the applied world, okay? So yeah, thank you very much. So you guys want to have your break? Have you drunk something?
We'll just take the chair here.
So we'll take the chairs, and maybe if you guys already have questions, if not. So when you have a question, maybe stand up and speak clearly, and that should be it. Do we have a question already? Does anybody want to go? Or should I start? What?
Thank you for the presentation. I have a question for Matthieu. Actually, in how much time the system is able to detect the false start in competition, and your system, how long is your computation of event detection?
Yeah, so currently it's near in the competition. It's nearly in real time. So as you can see when you watch on competition on the TV, so they just leave the block and they already get the answer. And currently my algorithm can work in real time, but I don't. After it's not the same system. Here I just run the code on Air softwares to be able to do it. So it's not working in real time. But if you want to implement it in real time, you have to build the system and to build the environment to be able to do it. But when I create the algorithm, I create it with in the mind that this algorithm should run in real time. So it's just a question of building the stuff to be able to work in real time. But yeah, so to be used in competition, you have to have something that is very quick. And for this reason that even if it's based on optimization method, it defines different options. It's quick enough to be able to be implemented in real fight competition. So it means that we have one criteria that we have to keep in mind. It's to have something very quick. So at the end of my PhD, because it's kind of being a new topic, maybe we're thinking artificial intelligence can do the job well, but there is this time constraint that maybe will not be able to work in competition because you will have to have like instant response to be able to say this is false start.
I'm interested in why the TA is one of the fastest responding muscles if we're trained to plan to flex.
Yeah, I guess it's something that at the start of the PhD I thought first initial action was going to be plantar flexion in the block phase, but when you look at it, when you break it down, athletes push back against the blocks, forcing themselves into dorsiflex. It's almost like even in passive dorsiflexion, you have your rectus femoris hip extended, psychology zero, and dorsiflex. Another thing I saw coming from my PhD is that the range of dorsiflexion depends on the block face lengths as well. It's different competitions, you have different block face lengths. It might be a short block face length, it might be a longer one, which would prevent that dorsiflexion or the range of dorsiflexion and the actual block length.
So is there a setup for your blocks that minimize the risk of false starting?
That's a good question.
From a practical experience, yes, I can say that. But experimentally, what we can say is that if the foot is pushed over back into the block face and you have long pedals so that your heel is touching, you'll notice that elite athletes are now using these big block faces and the heel will actually touch. That means that there's tension in the muscle before they actually exert the final force. And I can illustrate that if you imagine you have your finger, right? And I try to move my finger out, flick it out, okay? I can only move it so fast. if I put tension in these muscles here, look, it can flick very quickly. So you get athletes are pushing into the blocks to reduce the amount of time that they delay in generating a movement because they are pre-tensed in the blocks. And in that sense, we know that pushing against blocks is going to reduce delays. Delays, in fact, the muscle, the ankle will not have to dorsiflex much more. It's actually going to push against the blocks and propel movement, so you get a more rigid ankle. And I think the tibialis anterior, even though it's a dorsiflexor, it's actually stabilising for the gastrocnemius, so you have co-contractions.
Same as the RF.
Yeah, so you're going to get that anyway. So the fact that there's a little difference in TAs first, I don't think it's a major thing. What it is telling you is that these are acting, early.
Don't be shy, I know what it was before.
On the question that you asked about Matthieu's algorithm, one practical way of describing it is that when we did the test and demonstrated the system in a practical way with an athlete, most of the time was taken where the sound went, the athlete stepped out, came out of the blocks. The time delay that took place in processing was mainly you getting the file and dropping that into the MATLAB program. But the MATLAB program, once the file was visually sort of dragged and dropped into there, the pictures of the graphs came up and the solution were up in fractions of a second. So we know fine well that if we take out this operation of waiting for the file to store, then be dragged and dropped onto the algorithm. If you were to take that bit out, which is the longest period of processing time, that you'll be able to do it in less than half a second, I would think, which means that the athlete won't have taken more than a step before the decision would be made to make a lead call. So I think the algorithm is quick enough to run in real time, and there's good reason to think that.
What is the effect of the recent super spikes that are more compliant in the insole on that? Because that would add to the delay.
We could do.
Can you learn to use those?
There's two things about the super spikes. Does anybody know? Have you seen the super spikes that they're generally called? There's been a major change in athletics in the type of shoe that you can have. So spikes used to be made with a plate, an outer sole, and very little midsole. So the plate was reasonably hard, and then there'd be just a little bit of cushioning inside. But now what happens is that if I've got ordinary training shoes on, running shoes, there's a midsole, the white bit here. So the super spikes have got a carbon fibre plate, which is very, very rigid, and the spikes fit onto that. But before you get to the upper part of the shoe, you've got a midsole. And the midsole tends to give some shock absorbing. Nike use a bubble, an air bubble, and that tends to burst, and then they replace them. So if you've got a big athlete, they tend to burst the bubble, don't they?
Yeah, very quickly.
Pretty quickly. New Balance have got an EVA midsole and then the carbon plate. Adidas are pretty much similar, just slightly different alignment. So in answer to your question, the midsole material will tend to delay because it's not soft, but it's softer than the outer part of the spike plate. But the spike plate itself will give a rigid platform. So you've got a compromise, one giving a rigid contact and the other giving a bit of shock absorption, which will give a little bit. So I'm sure there's a little bit of delay, but there's a benefit by having a very rigid spike. And if you look at the spikes of 5-6 years ago, you could bend them. You could bend the sole, the outer sole. Now you can't.
It depends on the athlete as well. If you don't have a strong enough plantar flexor or muscle tendon unit with these really strong, rigid spikes, you're going to struggle. Even anecdotally, we see with athletes that, if you heard those in our group, that they're not that strong in that area, so you have to move more toward the middle distance spikes, which are more foam cushion as opposed to the carbon fiber plate. So it just depends on the muscle demands as well. It's placed, if you're strong enough to overcome those spikes.
I mean, we have exactly the same experience in the group that I coach. So some of our sprint athletes will wear what's designed as a middle distance spike because they need shock absorbing, and others would go all for the carbon fibre with minimum shock absorbing. But if they do that, they may well get lots of impact related injuries, the skeleton. So yeah, I think there's a compromise, and overall I think the spike plate, the new spikes are really it's quite funny when I look back in my own experience. A long time ago, I did compete in athletics, and I was a long jumper, and I would wear what used to be, these were Puma long jump spikes, and they had a midsole, they were the built up midsole, and they had an outer protective, fairly rigid outer sole. And I would say that new super spikes are generally like my old Puma long jump spikes. And it's funny, technology, it's taken all those years to get that benefit, and there's no spike that's perfect for all sprinters. I don't think that's the case. I think people are beginning to learn that they bring properties that are useful to athletics, and they have to be matched to the particular athlete. Some athletes will actually, the skeleton will shock absorb by pronation of the ankle joint complex, and others are fairly rigid ankle joint complex, and they need a bit of shock absorbing, and then they need to midsole. It's pick the spike that suits you. I'd say looking at spikes is a really interesting area of research to consider. Lots of people are beginning to get interested in it, but it is something that people are really interested in. And one other thing I would say is good research needs a good idea. Paramount. Have a good idea and follow it through. Sorry.
It's not very technical, but is the internal federation is able to understand the actual limitation of the 100 reaction time, and maybe how long does it take to maybe change the actual system, because maybe they are not very happy to change all the systems that they developed for years.
I suppose that's a question about influencing change.
Yes.
There's a lot of things in that question that I could look at.
Okay.
Imagine me coming along and saying your 100 millisecond rule is wrong, and here's the evidence. The organisation may start to worry about legal cases being taken against them. This athlete was disqualified, and argue that they've been disqualified unfairly. Now they can deal with that because they can put a moratorium and say, look, what's done is done. But that would be a consideration, that if you move the reaction time down to 70 milliseconds, people were disqualified, and the 91 millisecond false start, you could get legal cases saying, well, I get disqualified for 90 milliseconds, but we know that there's differences in the technology, so it throws a lot of complexities in to the whole thing. And you're possibly correct. It will take a lot of evidence, quite rightly, for world athletics to bring about a change. What we think is that they need to do this, because the current situation is not, this is a personal view, but it's based on what I look at. The current situation is no good for anybody. It's no good for the sport, it's no good for the athletics, world athletics, and it's no good for the athlete. Everybody's got an argument about it. So the current situation is not satisfactory. But there's no point in replacing the current situation with an equally bad solution. It needs to be a very robust solution. So I think it will take a long time, in terms of years, 4 or 5 years. If World Athletics are convinced that hand response time is the way to go, it will take them time to pilot that in major competition and across many countries before you can then justify a change in the rules which lowers the response time and implements new technology. So I think we would have a lot of work to do. And more than that, I think Limerick can't do this on its own. We need the companies to buy into it. We need other experts to come on board, because the team that we have is quite small, and we don't have all the best skills that are available in the world. So we need to throw this out and see if there's more expertise. And I see expertise in Rennes. I'm sure it's there, which could help us move that project on. To think that one person is going to have all the skills to deal with the algorithm development, the hardware. I mean, we've only used steel and sensors. We could use a composite material, like carbon fibre. It may be better to mount the sensor or something like that. It would be lighter, it would be more durable, and it would possibly be better, but we don't know that. There's a lot more work to be done. So there's a lot of dimensions to your question. Does that help? Does that answer help you?
Definitely. Okay. And just to know, for like the first studies that show sprinters were able to react before 100 milliseconds. It was 2007, I think. So 15 years, it's made like 15 years that we know that this rule is wrong, and it's still here. So after, like Drew said, that there is some trigger that can change. So for example, it makes a lot of noise, the false start of Devon Allen last year. So maybe this will start to change, and maybe, like Drew said, it's when the athletes will maybe sue one time World Athletics that it will change. You have the example of Chris Froome when he was caught for doping. He said, oh, the rules is not fair, and he get very good referee? Lawyer, sorry. He get a very good lawyer, and they change the rules. So if one day it's happened in athletics, I think they will have no choice to change the rules, because all the science-based, all the science behind said what you are doing is not really right. And currently what it's hard also, it's hard for World Athletics because yeah, they know that it's not perfect, but there is also no solution, no perfect solutions that currently exist, and it's what we try to do, to provide the solution, because it's easy to say it's wrong, but after what we can do. And this is the main part too, to try to develop a solution that is fair for the athletes.
One thing about it that was really important for me, particularly because I was out at the World Championships, and after Devon Allen's race, the next morning, I get this phone call. Now, I don't normally take phone calls. I didn't recognise it, but it was an American number. And somebody had told me, people are wanting to talk to you. So I took the call, and it was a magazine, a big magazine in America that wanted comment. And I know that it was really important not to criticise World Athletics. they wanted me, basically they wanted, as press do, they want a story. That's what they wanted, a story. They wanted sensationalism. And I tried to be very, very careful, and I said that I completely understand the situation that World Athletics find themselves in, because they can't fix it. They rely on the technology companies to basically come up with the science. And the people who are falling short in it are actually those that are getting a lot of money and providing a response time, and it's not giving them the best and most reliable solution. So everybody wanted to criticise World Athletics, but I basically said that I don't think it's fair to criticise the governing body, because everybody around, that's the scientists and the people who provide it, have to look at themselves and say, have we given you the solution? And I just don't think we have. And I think that's really important, because if I'd have said, yeah, the World Athletics, they've got it completely wrong, we've known for years, all these social media things were going around, I don't think we would have been able to get Seb Coe on side. There's no way that will happen. We need to be careful.
Correct me if I'm wrong too, but World Athletics seems to be one of the more open to science federations, since also the Pistorius case, they've actually appealed to independent scientists. It's my perception at least.
They have, and I think it's a sport that tries to be objective as possible. But it's not easy. I mean, they've tried some things and they've not worked very well. I mean, you've seen some of the measurement techniques that came in over the horizontal jumps, and they tried the technology to try and enhance the camera of the sprint start. That was a big mistake, because that didn't come off at all, which was, they're trying things to make the sport more interesting, but also to try and make it fairer. And it's difficult. If we go out there and criticise the organisation that's trying to improve things, they won't listen. So it's important to say objectively, this is what we found.
Maybe to continue on a similar vein, but every change of rule brings about a set of unintended consequences as well. It's difficult, but what could be the unintended consequence? Is it also possible to learn to play within the new boundaries, if that was to happen, if hand-based measuring was starting to take over? What could be the future of that?
I think if you look at the history of the whole thing, 1935 there was a patent for a hand response measuring system. It was basically a switchblade. Now that wouldn't work because it wasn't measuring force, it was just measuring when the switch went like that, so it was measuring movement, so that's a problem. But it's interesting that we knew back then that measuring hand responses was actually quite important, because the hands come off the ground before the feet. That's where that came from. If you look at other things in history, like where did the 100 milliseconds rule come from? Well, what actually happened was that IAAF, as it was then, had a meeting. I've seen the minutes of it, and they basically gathered data from one study, which was done in about 12 Finnish athletes, together, which was reported, together with the measurement of the reaction times in the Olympics prior to that. And they looked for the fastest reaction time that they had found. And it was around about 109, 110 milliseconds. And then they said, and it's in the minutes, then they said, But what if an athlete comes along who's going to be able to react faster than any that we've actually seen? Let's make it 100. And that's where it came from. Now, if that's how you make your objective judgment of what minimum reaction time is, we can't be surprised about what's happened now. You know, we can't be surprised about it. It was picked out of, yeah, let's do that. We need to have a much more scientific evaluation. I don't know if what we've been doing has actually got there. I think we need to look at the theory, and one thing is clear that I'd say all three of us would agree. You can't wait until, you can't reduce it forever to 20 milliseconds or 10 milliseconds. There is a delay period. You know, if it's 50 milliseconds, 50 milliseconds is half a meter, right? It's 50 centimeters in terms of an advantage of an error. Do you know what I mean? So there's a responsibility here which translates into distance. And if somebody says, look, we're not sure if you won or not, yeah? If we're going to let this person get a 50 millisecond advantage on you, let's set you half a meter behind you and, you know, and see how you feel about that. You wouldn't want the races to become setting off at different distances. That'd be silly. But that's what in effect is happening. We do need to have a more objective idea of what the reaction time is. If you go to a psychologist who's looked at reaction times, it's over 200 milliseconds is the value they quote. And, you know, simple reaction time. So if I go into a psychology paper and look at reaction time, they're talking about the reaction time is probably around 200 milliseconds. Well, we know it's not that. So the literature needs a lot more work. And I think we can have a statistical approach to try and predict it, but that has to be based on the right technology. Or you can back that up with some other measures, like we've seen Evan trying to find out what are the ranges of the electromechanical delay. What is the minimum time period for the signal going? Can we get some information from experimentation in nerve conduction times? I think, and distances and nerve conduction velocities. That's where we need to go. That undoubtedly is where we need to go to back it up and then say, this is the best science that we've got. Sorry, I can't hear you.
Questions for everyone. So first, congratulations for the research.
Thank you.
I have a question about your sprinters versus runners.
Yeah.
So the first question is, do you think results will be similar, let's say, sprinter versus a sport where there is a mix of sprint and swimming, like football, for example? And my second question was about the long-distance runners. Do you think that foot strike pattern will affect the result as well? Let's say that someone will bend on the forefoot or strike will have different forces implies.
Yeah, so the first question on if you had someone, say, who was doing explosive type training, I think you see a lot similar, much more similar group differences. Obviously, I think for sprinters, they've been trained, this particular group, national and international level, they've been trained for at least 8 years, so they've had repetitive exposure to explosive type training. Do you think if you had a group, so let's say soccer players who are engaged in some sort of sprint training, you would get those adaptations? Again, you have to track them over a few months, a few years to see exactly. As I said, we just measured this as one time point comparing that sprinter group with the physically active who we knew weren't doing any kind of explosive type activity. But I think if you see from even the research, explosive type training, sprinting, plyometrics, gym work is going to induce these adaptations in that particular muscle group. It's actually an interesting point then about the foot strike pattern, because as we saw there for the maximum strength of the dorsiflexion angle, we think that sprinters have a higher value because of the event-specific demands placed on them. So again, it will be something interesting to look at. I can't give a definitive answer, but I do think that if you have an athlete who's regularly exposed to a certain position where they have to develop high forces, depending on the foot strike pattern, you probably would see similar results. I think, yeah, definitely something interesting to look at. Thank you.
I had a question about what makes sprinters able to anticipate the gunshot. Are maybe the orders a bit too stereotyped? Because, I mean, I think the rules could be like no reaction time, not under 100 milliseconds, but just nothing, but more variability between the last order and the gunshot would prevent athletes to anticipate and maybe.
Okay, we had a really good discussion when Sevco was over, and it just shows how open they are to trying to find a solution, and we were open to this. We said that what if we had a countdown method where the athlete knew when they were going to start, and you disqualified somebody who went before the instant of the start. So the question was, what if we went little bleeps that went 3, 2, 1, beep, and on that long one, starting that long one, they could go. So we went into the lab, we said to Seb and Piers that we would go in and set that up, and we did, didn't we?
Yeah.
We thought that would eliminate the 100 millisecond rule. And I mean, it's an interesting thing because I think Seb was quite surprised. I said, if we could do that, I'd be happy. You know, we spent years of work. If we found a solution that would negate the point of having any kind of hand reaction or whatever, but we'd keep that anyway. So we went in and we set it up. Now we need to do more subjects, okay? But we set it up. The athlete anticipated, because he started activating before. So if I say to you, here's a tap. You can match it. We're able to do that. But in order to do that, this anticipates what this is doing. And so the muscle's actually activated to match the event. Do you follow me? They actually activated and the force appeared. Actually quite a long time before. And we could investigate that a bit further, but there's another avenue for research, you know, where we could take a big group. We actually have set up, we've got a master's project, haven't we, with the title? Yeah. And we're waiting for our sports performance master students to buy into that. So in Limerick, we set up our same system and we set up it doing a countdown.
It's like Formula 1.
Bit of Formula 1. And Seb's answer was if we could get rid of that, because the controversy is 100 milliseconds. Unfortunately, the initial evidence is that it might not work. But we did say we'd follow it through, and we will. So that's it. I think we just have to think a wee bit out of the box, as we say. And if somebody says to me, oh, you want to promote your fast system, for me as a researcher, I want a solution to an unfairness more than I want to see our system making it to, you know, and that sounds really strange, but for me that's what motivates me. I was motivated to do this because I was an athlete, not a very good one. I was a coach, and I see unfairness, and we need to do something about it. And there's no point complaining if you can do something, but equally there's no point trying to promote a vested interest of mine. That's not going to solve the problem. So that's one that we could set up here as well. Would that answer the thoughts you had?
Yeah.
Actually, now you mention it, in skiing, they've gone the movement pathway, and there's a technique to start before starting, before moving the little gate, and
So the idea would be that you only disqualify people who blatantly exert force before the start command. And I think the indication was that you were one of the people who was doing it, you couldn't do it.
Not a great starter at all. But
Can't anticipate.
yeah, I was convinced that I was starting normally, but each time I was before the gun. Even tried to go slower, which is, it's still frustrating.
We need to investigate that a wee bit further.
and swimming, where you've got the whole platform. Yeah.
Maybe a question from Matthieu, all of you. International Federation or World Athletics, will they agree to change all their system with the cost of, I don't know how much cost for space used, but change all system all around the world for all competitions? Will they agree to do it? I don't know.
I think the governing body has got a right to make the rules. So I think at the moment, what was really funny was I put that slide up of Stephen Wilwatcher's work when Seb was in Limerick, and he looked at it and he just said, "When did that happen?" And I said, "Look at the date. It was 2013, was it?" Yeah. And there was relief because he said, "Oh, that's before you became president." You know, he said, "Well, yeah." He said, "But you can't have systems out there that are not fair." You know, so basically what we're saying is that you go to European Athletics Association, right? And you go to the World Championships, and you imagine the same athlete, you know, with a reaction time. In the European Athletics Championship, the same reaction would be a different reaction time from it would in the World Championships. That's what's happening. They also know that in Oregon, something was done to the system, wasn't there?
Yeah.
They gave me the data. Something's been done to the algorithm. Can't be anything else. But Seiko have not told them what they did. So it's really imperative that the governing body is in a position to tell the suppliers of the timing system, we want the following regulations in place. And that was the main drift of your recommendations in that paper, wasn't it? It needs to be regulated.
After what for people who don't follow athletics, so what happened in the last World Championships that during the first day, in every race, nearly every races, there is some false start. So there were a lot more false starts than usually. So it was not normal. So as Drew and Evan said, that for sure I think they reduced the sensitivity of the threshold, but without knowing antibodies. And you know, athletes with all the practice that they do, they are close to the limit, so they kind of know the limit of the system. As you said, oh, is this system like I know if it's sensitive or not, and I can try to play with the limits. And because they change the algorithm, like just without saying anybody, without saying anything to anybody, and especially to the athletes, they never do some sprint start in this configuration. There were a lot of false start, and it was funny that it just lasts for 2 first days. So I think after they put the last threshold, because it was like a mess, too many false starts. So it means that it's the companies that keep the box secret, the black box, and here, like, the World Athletics were the victims. So I think if we can show road athletics that we have a system that is more fair, they will accept to pay. And after, this is another point, but what is funny is that I think, Drew, maybe you know, but the current start information system is very expensive. And the solutions that we provide, but we need to improve it maybe with carbon fiber and everything, but it will be cheaper than what is used usually because like one strand gauges is not very cheap, it's just one wire, a very thin wire that that we need to bring some power in the wire, so it's not, it will not be very expensive. So I think if we prove like we have a system that is more fair, for sure that they will be happy to change it.
I was given the privilege to see, it's not private, it's not secret. World Athletics hold all the reaction times of all the competitions, so they become public knowledge. But they sent that information to me and said, what do you think, what's causing this? The reaction times in Oregon had gone down. There were shorter reaction times in Oregon than there had been in previous competitions. Now if you go back in history, as soon as they made a rule change to make it used to be 3 false starts, you were disqualified. Then it went down to 1 false start, and each athlete was allowed 1 false start. And then it went down to 1 athlete can make a false start, and then everybody's on a warning. And each time they went through that rule, the reaction times became longer, and they've been staying longer because the rules are quite strict. And suddenly, Oregon had gone down. The question was, how can that happen? Had to be something that has been done to either change the technology or change the algorithm. I don't think it's changed the technology.
We got time for more questions if you want. If it's
Can I just say thanks for having us? It's been a pleasure for all of us to be able to talk to you about this in such an open way, and thanks for your patience for sitting through in a warm room for so long.
Thanks for your time.
Thank you.
Well, thank you very much. Merci. Si vous reste des questions, quoi que ce soit, vous pouvez envoyer des emails. Je vais éviter de faire ça. Vous pouvez m'écrire. Vous pouvez aussi écrire directement ce que vous avez lu, dans le respect du temps, et puis c'est ça que je vais répondre. Mais voilà, donc merci beaucoup d'avoir participé. Le séminaire sera disponible donc sur la chaîne YouTube de DIGISPORT. Si vous avez manqué des passages, ou s'il y avait des choses qui étaient claires. Vous avez un certain nombre d'articles aussi pour les étudiants sur les espaces cursus. Voilà. J'espère que ça vous a plu. C'est une opportunité rare d'avoir des gens comme ça qui nous donnent de leur temps et qui font partie de